Hello, everyone, and welcome to the second live session of our four-part webinar series, Design of Facade Attachments, presented by Alex Zimmer. Today is May 16th, 2019. I'm Nate Gonner with AISC, and I'm your moderator for this webinar series. I would like to welcome back our speaker, Alex Zimmer. Alex Zimmer is a senior project manager with Simpson Gumpertz and Hager in Waltham, Massachusetts. He joined SGH's structural design group in 1998. He designs new building structures with a focus on new academic and healthcare buildings. And he also investigates and rehabilitates existing buildings and other structures. Mr. Zimmer earned his bachelor's degree in engineering from Swarthmore College and his master's degree in structural engineering from Stanford University. Alec worked with SGH Senior Principal James Parker to develop AISC's Design Guide 22 on facade attachments to steel-framed buildings. And he has presented on this topic for AISC around the United States. Alec, thanks again for being here, and I'll now turn the floor over to you.
Nate, thanks for the introduction, and welcome back to those who are joining us from last week, and welcome to those who are joining us for the first time today. My name is Alex Zimmer. I'm with Simpson Gumpertz and Hager in Waltham, Massachusetts, and we'll dive right in here. So hopefully you've had access to the pre-recorded session on fundamentals of facade attachments. And last week we covered a number of different facade systems, including transitional masonry cavity walls, panelized facade systems, aluminum glass curtain walls, and how to size joints for vertical movement. Today we'll be talking about slab edges and spandrel beams, and a quick word at the very end about supporting cladding away from floor levels of the building. So let's dive right in and start discussing slab edge conditions. The slab edges are where the facade meets the structure, and they can be some very finicky details to resolve. There's a lot of construction costs associated with these details, and relatively minor architectural and structural differences can have a substantial effect on the constructability of the system. So slab edges deserve a lot of consideration early on in the design process, and let's start talking about them right now. So there are a number of factors that influence how we design the slab edge, including the weight and the type and location of the facade system. In other words, its position relative to the spandrel beam, whether you have a backup wall that's supported on top of the slab edge or maybe runs by it, how long the slab overhang is, what the flexural and shear capacity of the slab or deck is, and how the facade load is applied, and consistent conditions. And although I've put it here as last on the list, by consistent conditions, what I really mean is how consistent the slab edge condition is around the perimeter of the building at each floor level. Similar slab edge conditions throughout the project can lead to economy and easier inspection, while a variety of different slab edge conditions can make everyone's lives complicated and expensive. There are two fundamental approaches to designing the slab edge, and we'll dig into these here in just a few minutes, but let's introduce the concepts first. So in approach number one, the slab or deck cantilevers beyond the spandrel beam and transfers a gravity or vertical reaction to that spandrel beam, but doesn't impose any twist on it. In option two, the designer doesn't want to count on the slab or deck, or can't for whatever reason, and therefore all the load that's in the slab edge has to be transferred to the spandrel beam as not only a vertical load, but a twist as well. So there are a number of factors that influence one's choice of how to approach the slab edge. First and foremost, does the slab have the capacity in flexure and shear to support the facade? In many cases, it may be uneconomical to increase the thickness of the slab for strength just to support the facade loads. So does it have enough capacity to start with? Are there issues with the quality of the concrete that you might be concerned about? Or are there depressions behind the spandrel beam as you see here, or maybe even an opening behind the spandrel beam that would limit the slab's flexural or shear capacity? And also we need to think about what attachments the facade has and how you're going to attach the facade. Are you going to attach it to a bent plate directly on the slab edge, or are you going to hang it somewhere below the spandrel beam? So let's dig into approach number one. This is with the slab cantilevering beyond the spandrel beam to act as essentially its own beam, spanning between the spandrel beam and the next interior adjacent floor beam. So let's walk through this figure. Starting from the right, we've got a facade attachment. In this case, it's graphically shown as curtain wall, but it could be any number of different options. The facade system applies a vertical load and a horizontal load directly to the slab edge, and the slab edge transmits those loads to the base building structure. In this case, as a beam acting in flexure, applying a reaction to the spandrel beam, as you see here, and dragging horizontal loads into the floor diaphragm. Now, when you look at this as a beam, don't forget that the cantilever action creates a significant amount of negative bending moment over the spandrel beam here. And so unlike when we typically design slab on deck as a simple span between adjacent beams, in which case you concentrate on the flexural capacity as a function of the reinforcement, in other words, the deck at the bottom of the beam. Here you need top reinforcement in the slab to address the negative moment due to the facade loads. And looking down below, you see the moment diagrams for this condition. You have a positive moment due to interior loads on the floor that looks something like this, but you have a negative moment over that spandrel beam that looks something like this. And these may not cancel each other out. You may need to develop a fair bit of negative moment reinforcement in the top surface of the slab well into the span. So the design of the slab needs to consider the orientation of the floor deck and the effective width of the compression block in the concrete for flexure, and also the effective width of that slab for shear. When the deck is perpendicular to the spandrel beam, the effective depth of the slab is the full thickness of the slab, but the effective width of the compression block is just the width of the concrete between the flutes. So in other words, if I have a 6-inch or 6 1/4 inch thick lightweight concrete slab, as I might on 3-inch deck, the effective width of the compression block is really only the width of the concrete that occurs below the top of the flutes in this zone. In contrast, if I have the slab running parallel to the spandrel beam, my effective width for compression is the full width, but the effective depth is greatly reduced. I can really only rely on what's between the top of the deck ribs and the reinforcement that I place near the top surface of the slab. We should consider also how the facade loads get distributed to the slab. In our practice, we typically consider the point loads on the slab edge to be distributed at a 1-to-1 slope away from the area in which they're loaded. And that gives us 2 effective widths along the spandrel beam, one here on the outboard edge of the spandrel beam and one here on the inboard edge of the spandrel beam that you need to consider when you're looking at shear and flexure in the slab. This 1-to-1 slope that I'm showing here is not codified, it's not set in stone, and so the designer can make judgments on what the appropriate effective width is for a given situation. I'll add here that Design Guide 22 includes a number of design aids for determining the slab flexural capacities for a number of different reinforcement types and spacings, for a number of different slab thicknesses and deck thicknesses as well, and deck orientations. These were based on ACI 31805, which was in effect at the time that we prepared the design guide, though I believe they're still valid for ACI 31814. You'll notice also that we're not listing welded wire fabric as reinforcement in the slab. We generally prefer using deformed bar or bar mats in slab rather than welded wire fabric, because we found that welded wire fabric can easily be damaged during construction by people walking over it, and so it gets deformed easily, and it also gets pushed down toward the deck, where it does little good in resisting the negative moment that we have over the slab. Over the spandrel beam, excuse me. So we really prefer using deformed bar in this case and making sure that bar is placed near the top of the slab to help us resist the negative moment. A quick word here about closure strips. Just be aware of what your closure strip condition is, and if you're relying on the deck for in-plane shear capacity as a diaphragm, the continuous closure strip may limit the amount of in-plane shear you can transmit to the spandrel beam. So that's the end of approach 1. Let's talk about approach 2, where the slab cantilever does not resolve the eccentricity. So in this case, we're not relying the slab as a beam. We're going to transmit all the facade loads, this vertical component FV and the moment MEF, through a bent plate or some other hardware that transmits the loads to the spandrel beam. And again, here are the keynotes to that previous figure. And throughout the presentation today, we've incorporated a lot of figures directly from AISC Design Guide 22. And rather than including just the figures, we're also including the keynotes on the next slide. I won't take the time to go through these today, but you'll see these come up throughout the presentation today. So some strategies when dealing with approach 2 when we're not relying on the slab's flexural capacity. As we mentioned, this imposes both vertical forces and twist on the spandrel beam, or torsion. And some strategies for dealing with the torsion on the spandrel beam are trying to have a rigid bracket like this on the back of a panel. For example, this is a precast concrete panel, and so this bracket has to be designed for a moment on this interface here between the panel and the bracket, and the idea is that this connection is essentially a pinned connection. Be aware that if you have a tie back, as you see here, this may impose some twist on the spandrel that you have to account for. You can also provide a kicker brace going from the bottom flange of the spandrel beam up to the deck to help deal with the torsion, or maybe providing a roll beam, in other words, a floor framing beam that frames into the web of the spandrel beam to help resist some of that twist. Or perhaps the span is short enough where you can just deal with the torsion and the warping normal stresses in the spandrel beam that result. And we'll talk more about how to design the spandrel beam later today. One of the least expensive ways to create a slab edge is to use a gauge metal pour stop. These are typically 12 to 20 gauge material, light gauge material, and they're typically field installed and welded to the spandrel beam. And this allows a lot of adjustability in the location of the slab edge if for some reason the location of the spandrel beam happens to be off of its theoretical center point. So these are relatively inexpensive, and they're simple to adjust and erect, and they're typically used when we have a slab overhang that's clear of the spandrel beam flange of less than 12 inches. In this case, the slab itself, the concrete, will have to have the strength to support all the superimposed loads, and the facade attachment load has to go directly into the slab and not through the pour stop. The pour stop is typically not strong enough to accommodate supporting the facade loads directly. So in other words, the pour stop is just that. It's a stay-in-place form for the wet load of the concrete. When we design light gauge metal pour stops, we typically need to consider the wet load of the concrete, the construction live load, and the cantilever beyond the flange tip. We could go about doing the calculations for this, or better yet, we could go and look at the Steel Deck Institute's Pour Stop Selection Guide, which we've reprinted for you in AISC Design Guide 22 with SDI's permission. One quick mini case study from one of my own projects where I had a fairly long slab edge. In this case, the slab edge was on the range of 18 to 20 inches from the tip of the spandrel beam. And in this case, we really wanted to use a light gauge pour stop here to try to simplify erection. The perimeter of the building happened to be curved. And we provided a flat plate that was essentially an extension of the flange of the spandrel beam, and we provided a full-depth stiffener to support that. So the flat plate in this case spanned parallel to the spandrel beam between the stiffeners, and we provided a light gauge pour stop with plus or minus 2 inches of extension beyond that flat plate to allow for easy erection and adjustability. So when we design the slab edge itself with a structural steel bent plate, because we have a long slab overhang, or because we are using approach number 2 where the bent plate has to take the facade loads, there are a couple of cases we need to consider. One is with the pour stop acting essentially just, the bent plate acting just as a pour stop. So the slab itself would take all the superimposed loads and resolve the eccentricity as we talked about in approach number 1. So again, the process for designing the bent plate as just a pour stop is just as it is using the light gauge metal pour stop, using the same wet load of concrete, construction live loads, and understanding what the cantilever length is, and trying to control the deflection of the pour stop so we don't get excessive concrete in the edge of the slab. And just as SDI has done, when we were developing Design Guide 22, we developed a couple of tables, as you see here, for selecting a light gauge pour stop using designing a hot rolled steel bent plate pour stop for a variety of slab overhangs and slab thicknesses. And we limited our bent plate thickness to 3/8. So in the second case, the designer might not want to count on the slab acting as a cantilever beam in approach 1, but does want to weld the facade to something more substantial than a light gauge metal pour stop. In this case, the slab still takes the full design load, but we need to transmit the loads from the facade itself into the slab using the bent plate, as you see here. So when the bent plate serves as both the pour stop and the means of attaching the facade to the slab edge, the facade loads must be transferred from the bent plate into the slab. And there are a couple of ways to do that. One of which is to install an embed or something like that directly in the top surface of the slab to engage the concrete, or you can apply a headed stud or maybe a deformed bar anchor on the vertical leg of the bent plate that you can use to drag the forces back into the slab. And the design of those headed shear studs needs to be consider the edge distances and spacing between them. One quick word on using headed studs on the vertical leg of the bent plate is that these may pose a tripping hazard to the iron workers as they're erecting the frame and setting the bent plate. And so quite often these tend to be field installed rather than shop installed, and that doing the horizontal weld to the vertical leg may be tricky, particularly if it's a very short vertical leg. In Design Guide 22, we've included a number of design aids for headed studs for both shear and tension in slab edges, so hopefully you'll find these useful. In the third case, where we have a slab edge with a structural steel bent plate, the designer does not have a slab, or because there's an opening adjacent to it, or perhaps there is no concrete slab on deck. Maybe it's just a simple, flexible, non-composite roof deck. And we somehow have to transfer those facade loads back into the spandrel beam. So in this case, the bent plate, or whatever other hardware you provide, has to transfer the load directly into the spandrel beam. So when you do this, you need to consider the fact that the vertical force gets transferred through bending and shear through the bent plate and has to get resolved into the spandrel beam. In this case, we have to consider the fact there will be torsion and a twist applied to the spandrel beam, and we either have to design that spandrel beam for the twist, or we have to restrain the twist using a kicker, as you see here, or perhaps a roll beam to restrain the torsion in the spandrel. A quick word on transfer of in-plane forces to the slab. As I mentioned before, there are a couple of ways to do that, one of which is to apply a headed shear stud on the vertical leg of the bent plate, as you see here. What I've been doing more commonly in my practice these days is applying a deformed bar anchor, which you see here, and you see in practice from one of my projects, welded to the vertical leg of the bent plate. So this doesn't pose as much of a tripping hazard for the iron workers, and allows a male threaded bar to be threaded into the female coupler that's welded to the bent plate. You'll also see in this photograph a very long slotted hole with the head of a bolt in it here. This allows the bent plate to be adjusted in and out, and when the final location is set, the plate is welded to the top flange of the beam. And that brings me to my next slide, which is bent plate fabrication and attachment approaches. There are a number of ways the bent plate can be attached to the spandrel beam. It could be shop welded, as in Figure A, or it could be shipped to the site with an erection bolt, as in Figure B below, and that's what you saw in the previous slide. Option A is by far the most economical solution, but it doesn't allow for any field adjustment, and for that reason, we prefer using option B, with the erection bolt and the field welded final condition, or perhaps relying on short slotted hole and slip critical behavior between the bent plate and the top flange of the spandrel beam is an option C. So options B and C provide you a good bit more adjustability in the field, whereas option A is probably the most economical of these three. And again, here are just the keynotes to that previous slide. So when you're planning the flange width of your spandrel beam, there's some things to keep in mind. First of all, whether you have a bent plate as you see here or a light gauge metal pour stop, you need to have some overlap on the top flange of the beam so that you get appropriate cantilever behavior of the slab edge, and you have enough room to make the weld. So you need probably 2.5 or 2 inches, maybe 3 inches here to make that connection. The floor deck itself needs to bear on the top flange, and maybe that's 2.5 or 3 inches. And you also need to have some clearance to fasten and weld the headed shear stud connectors to the top flange of the beam. The stud can be welded through the deck if you need some if the deck needs to be pushed in or the bent plate needs to be pushed in, but best to plan on some width here. When the bent plate pour stop is adjustable, that's even more reason why you need to consider this more carefully. The stud might need to be offset, and maybe the flange thickness might need to be increased to allow the stud to be offset from the web so that you don't have a burn-through problem, particularly if the slab edge is adjustable in the left to right direction. And as an example of what can go wrong with this type of detail, I'll show you one from one of my own projects. This is a case where the bent plate was shipped with a erection bolt and was to be adjusted in the field. And in this case, the erector, for reasons that escape me, welded the shear stud connector here to the horizontal leg of the bent plate rather than to the top flange of the beam. And when I got to the site and saw this, I quickly did some calculations and determined that the erector needed to add supplemental welds between the bent plate and the top flange of the beam here and on the underside as well to mobilize the capacity of the shear studs that we needed. When you have large overhangs, there are a number of ways to approach this. A couple alternatives are to provide a large stiffener, as you see here, and as I showed you in the previous slide. This allows the vertical forces in the facade to be transferred in flexure and shear through the stiffener and transmitted to the spandrel beam, and perhaps resisted in torsion through a roll beam, as you see here. A lighter alternative might be to use a kicker, something as you see here, to take the vertical forces and transfer them to the spandrel beam. And there are many other ways to resolve this eccentricity as well. There are a number of examples in Design Guide 22. We're not going to have time to dig through all of them today, but I am going to focus on example 5.6, which is the design of a bent plate slab edge with a welded bar coupler that transfers the facade loads. So let's dig into that. So in this case, we have a bent plate pour stop supporting the facade, and slab flexure and shear capacity themselves are ignored. So we're going to have to transfer the loads from the facade through the bent plate to the spandrel beam. The spandrel beam will have to be designed to resist those in torsion as well. So the only thing we're going to rely on the welded bar coupler for is to resist out-of-plane forces, the FH forces, as well as a component of the moment from the vertical facade load. So here's the problem statement. We've got a vertical facade load, FV, of 1.8 kips, and it's going to be applied at an eccentricity from the slab edge of 5 inches. This might be a typical curtain wall example. We also have a horizontal load, FH, of 1.8 kips, and that's applied 3.5 inches above the bottom of the bent plate. The bent plate itself cantilevers 9 inches, LOH, from the tip of the flange to the vertical leg of the bent plate. So we also need to design the weld between the bent plate, horizontal leg, and the top flange of the beam. In all cases, we're going to design the bent plate to resist all of the facade loads, apart from the horizontal ones, without relying on the concrete slab and flexure, and we're going to use A36 material. So here's another statement of the problem taken directly from the design guide. So let's move through some of the calculations here. So because the horizontal force acts through the vertical leg, that load is going to get transferred directly to the slab by the welded bar coupler that's on the vertical leg of the bent plate. But we do have to deal with the eccentricity of the vertical load from the facade, and that's MEF, and that's going to be equal to the vertical load of the facade. It's 1.8 kips at an eccentricity of 5 inches, so we get 9 kip inches per attachment point. And that has to be transmitted to the bent plate. So we're going to decouple that moment, MEF, which you see here, into a tension and compression couple. So the tension component of that couple is going to be MEF divided by EV. That's going to go directly into the threaded bar coupler and into the slab. And the compression component would go into the horizontal leg of the bent plate, as you see here. So for a strength load combination of 1.4 dead load, the required flexural strength in the bent plate, since we're not relying on the slab capacity, is 1.4 times the vertical load times LOH, which is 9 inches. So we have to design the bent plate at the critical section right here at the tip of the flange for 22.7 kip inches. That's for the dead load case. And now we have to figure out what effective width the plate has in bending. We're going to spread the load out at a 1-to-1 slope, as we showed you before. So in other words, 45 degrees. And we're going to assume that the point of application on the tip of the bent plate is effectively 0 width. So we get an effective width here on the outboard edge of the flange of 18 inches. And we're going to compute the plastic bending moment capacity of 0.9 times Fy of 36 times Z is 0.861 inches cubed, and again 27.9 kip inches, and that's greater than the demand of 22.7 kip inches. And just for reference, the plastic moment capacity is 1/4 times the effective width that we compute here, 18 inches, times the thickness squared. And we also want to compute the vertical deflection of the bent plate. Again, neglecting the contribution from the slab itself, and we find that's about 0.531 inches, which is less than 3/16. So for our example here, we're going to use a 7/16 inch thick bent plate. Now we need to design the welds of the 7/16 bent plate to the spandrel beam flange. Again, we'll take our moment demand of 22.7 kip inches, and we can divide that by 1.392. This is the capacity of a 70 KSI weld in kips per inch per 16th of thickness. We're going to multiply by 1.5 because the load is perpendicular to the axis of the weld. We're going to try 3/16 of an inch weld, and the length of the weld is 2.5 inches. The distance between the welds is 2.5 inches. And that says the minimum length of weld along the spandrel beam is 1.45 inches. So we'll use 1.5 inch long fillet welds at 12 inches on center in this example. We also want to check the load that has to go into the threaded bar coupler and into the slab directly. And we see here that we have the moment, which we've seen before, times its eccentricity divided by the vertical separation between the welded bar coupler and the horizontal leg of the slab. And we're going to add to that the horizontal component of the wind load, again factored for 1.2 dead and 1.6 wind. And we have to drag almost 5.8 kips horizontally into the slab through each threaded bar coupler. And headed studs could also be used for this purpose, perhaps with a candy cane type 180-degree hook bar in the slab, also a viable way to do it. For sake of completeness, we should check the horizontal leg of the bent plate and find that that takes 2.88 kips, though in practice, this is going to be resisted by bearing on the concrete slab. So that's our discussion on design of slab edges themselves. Let's dig into designing the spandrel beams. So designing a spandrel beam is a lot more than picking a wide flange section that meets the flexural strength and stiffness criteria which might come out of our software. It involves a lot of different design considerations. So some things that go into this are whether the spandrel beam is composite or non-composite, whether it's part of a moment frame, which might restrain vertical displacement and also restrain torsion at the ends of the torsional warping, at the ends of the spandrel beam, and whether there's any weak axis bending on the spandrel beam due to out-of-plane loads from the facade. So some general considerations for the spandrel beam design are what its pre-composite dead load deflection are, what its post-composite dead load deflections are from the facade loads, as well as any additional superimposed dead load on the floor, superimposed live load demands on the beam, whether the beam needs to be designed to consider floor vibrations for the occupants or sensitive equipment inside the building, whether there are any concerns about creep in the concrete on the axis of the compression flange of the composite section, and whether there are any weak axis loads as well that are applied laterally to the beam. Now, as I've mentioned a number of times today, a lot of the facade connections will impose twist or torsion on the spandrel beam. So how is that twist or torsion accounted for? Is it resolved at the columns? And if you look at AISC Design Guide 9, there are essentially two approaches to this. One is for what AISC Design Guide 9 Figure 3.3 calls a rigid support, which not only resists the twist at the end, but also has warping normal stresses associated with it, or whether you have what AISC Design Guide 9 calls a torsionally pinned connection to the column, which has torsional shearing stresses which are greater than 0 but has no warping normal stresses associated with it. So a moment-connected beam would typically have some warping normal stresses at the end, whereas a pin-connected beam with perhaps a double angle connection to the column would have no warping normal stresses at the end. But both cases resist the rotation at the end of the beam. So is it resolved at the columns? That's something to consider. Do we have kickers or roll beams that would tend to restrain the twist of the beam? And what effect do the rotation and the projected translations of our facade attachments have on opening or closing of joints in the facade system? So again, when we look at the column connections, are they simple shear connections that might not have any warping normal stresses in the wide flange? Or are they moment connections, which would have warping normal stresses that you need to add to any moment demands in the beam due to gravity loads and due to lateral loads? How are out-of-plane forces delivered to the column, and how are torsional forces restrained? Those are all things that we need to consider when we're designing the spandrel beam. Some general design considerations having to do with spandrel beam depth are having adequate flange width to accommodate the pour stop or the bent plate around the perimeter of the building, having enough real estate on the top flange to accommodate the headed shear stud connectors, as well as enough room to bear the composite deck. Making sure you have adequate flange width to accommodate those things, as well as flange thickness if the headed studs need to be aligned off-center from the spandrel beam web. And also trying to have some consistency around the perimeter of the building so that you're not having a variety of different facade support conditions as you vary the spandrel beam throughout the perimeter of the building. Remember that a net savings in tonnage by having varying spandrel beam sizes may not save the headaches and heartburn of trying to figure out how to support a facade at 24 different spandrel beam types throughout the building. You also need to consider whether the spandrel beam should be eccentric to the column center line to try to minimize the slab edge. Maybe, maybe not, but it's an important consideration to make. It may make sense to offset the spandrel beam from the column center line to try to minimize some of those eccentricities. If you do something like that, do you have enough clearance to make adjustments, and do you have enough room to get the bolts in a connection like you see up here to this column web? And what about fabrication and erection? Are we accounting for those in our spandrel beam design and our facade support design? Are we adding a lot of weight at the sake of making the connection simpler, or are we trying to make things as simple as we can and accepting the fact that our spandrel beam and all the associated hardware might be heavier than we would anticipate from our analysis software? Generally speaking, in the design of a spandrel beam, stiffness controls the design. We found that typically controls over the flexural and shear demands on the beam. But it's important to notice that if we have twist in the spandrel beam, we may develop warping normal stresses which need to get added to the flexural normal stresses in the beam. We also need to look at local stresses on the spandrel beam. So if we're attaching our facade to the flange, do we have any local flange bending problems associated with that facade attachment? So the appropriate deflection criteria for the spandrel beam really depends upon how much deflection the facade system can tolerate. The amount of vertical deflection the spandrel beam can undergo, for example, under brick veneer, might be limited to the span over 600 according to Brick Institute of America, but that spandrel beam deflecting may cause the shelf angle to deflect, and the sealant joint that's below that shelf angle, as we discussed last week, may have a tighter deflection criteria than simply span divided by 600. So we need to think about how the spandrel beam deflects vertically as well as how it rotates under the facade loads to determine what the actual deflection should be. So we need to really pay close attention to the rotation of the spandrel beam as well as the vertical deformations. We also need to think about the sequence of loading in terms of serviceability and what loads tend to close joints and what loads will compress sealants and cause, for example, brick masonry above to bear on brick masonry below the joint, and what loads are going to cause the sealant to squeeze out of the joint. So in the case of a spandrel beam like this with a brick veneer on it, you need to think about the sequence of loading. Which loads cause the joints in the backup to close, and which loads cause the joints in the facade to close. So in this example, loads that occur before the brick is in place on the building, and those loads would be the self-weight of the spandrel beam and the self-load of the slab, and perhaps even the self-load of the backup, will occur before the brick is even erected. So those loads we don't have to consider when we design the soft joint. We do need to consider superimposed dead loads that are applied after the sealant and brick are in place, and we do need to consider the live loads as well. So let's do a quick case study looking at deflection design for a number of different facade systems. We're going to look at, assuming we have a 30-foot long spandrel beam between columns, the superimposed dead load on the floor is 10 pounds a square foot. The live load is 100 pounds per square foot. We've got 12 feet from floor to floor. The tributary width on the spandrel beam is 5.5 feet, so it's 11 feet to the next interior beam. This is a true beam, that is to say it's not a girder picking up interior floor framing. We have a 3¼ inch lightweight slab on a 3-inch composite metal deck. Again, the deck is parallel to the spandrel beam, and we're going to ignore torsion for now. Actually, this should be perpendicular to the spandrel beam. Excuse me. We'll fix that for the next time. We're going to look at 4 different facade systems: brick veneer with a CMU backup, brick veneer with a cold form metal framing backup, a 6-inch thick precast concrete wall panel system, which also acts as its own backup, and an aluminum glass curtain wall system. And for right now, we're going to forget about torsion. We're only looking at vertical flexural deformations of the beam. So in the first case, we've got a brick veneer with an 8-inch CMU backup grouted at 32 inches on center. And if we place no deformation restrictions on the beam at all and only need to satisfy strength, we find that a W16 by 26 composite section works. It's got a demand to capacity ratio of about 0.93%, and we get some fairly large deflections. So the net total deflection is about 1¾ inches, and the deflection due to superimposed live load and dead load is about, say, 7/16 of an inch. If we limit the deflection to L over 360, we get a 16 by 31. And if we limit the superimposed dead load and live load deflection to 3/16 of an inch, as you might need to do to control the compression of the soft joint sealants, we find that we need a W21 by 62. So more than twice the weight per foot if we have no restriction at all. And the beam works with flying colors for strength. So we're really limited here by the deformation of the beam. So a similar system is brick veneer with a 6-inch metal stud backup at 16 inches on center. Again, we can get away with an even lighter spandrel beam. This time it's a W12 by 19 if we're only concerned about strength, but we still need the W21 by 62 for looking at the serviceability condition. And that is because we're really only concerned about controlling the deflections that occur after the slab is in place and cured. We're only trying to limit the deflections due to live load and to superimposed dead load. As an alternative, let's look at a 6-inch precast concrete panel cladding system. If we have no depth restrictions, we need a W14 by 22 to get the job done. If we're trying to limit the superimposed dead load and live load deflection combined to 3/8 of an inch, as you might need to do if you had a soft joint size between panels of 3/4 of an inch or so, you need an 18 by 40 to do that. So again, we're controlled by the stiffness of the spandrel beam. And finally, looking at the aluminum glass curtain wall system, if we're trying to limit the deflection due to the curtain wall load, superimposed dead load, and live load to about 3/4 of an inch, you need something considerably heavier. You need a 16 by 26 as compared to if you don't restrict the deflection at all. So from these examples, you can see that the design criteria for the facade itself can have a significant impact on the design of the spandrel beam and control the design as compared to the strength of the beam. So when we design for torsion, we need to consider the effect of where the facade load is applied to the spandrel beam from both the facade itself and in this case for the backup wall, which is shown here graphically as CMU. This is a brick veneer over a block facade system. So we need to consider where these loads are applied and how they impact the spandrel beam itself. So let's look at a plan view now of a spandrel beam. We've got columns here. The spandrel beam spans horizontally between those. The deck is spanning perpendicular to the spandrel beam. And we have a bunch of hangers between the spandrel beam that you see here and the shelf angle. So in cross-section, it looks something like this. We have the spandrel beam, some vertical hangers, and we've got a shelf angle out here. So as you can see in this diagram, when the spandrel beam rotates due to torsion as a rigid body, the hanger will also undergo a similar rigid body rotation, and the shelf angle will as well. So as the spandrel beam rotates, you get a vertical displacement due to the rotation of delta VRB. And similarly, you get a horizontal displacement of delta HRB, perpendicular to the plane of the wall. And these deflections need to be considered in advising the architect on sizing the soft joint beneath the shelf angle. As you can see, this is probably exaggerated, but it gives you the idea that we're trying to get across here that we need to consider the torsional rotations as well. One way to eliminate the torsion on the spandrel is to install kicker angles at each hanger along the shelf angle. So at each of these hangers, we have a kicker brace, as you see here, that address the torsion, and now the spandrel beam doesn't have to be designed for the torsion. But doing something like this may prove uneconomical, as a significant amount of structural steel is the project, and it's time-consuming to erect. So as an alternative to putting a kicker at every hanger location, you could consider installing a kicker only at select locations, maybe every 10 or 15 feet or so along the length of the spandrel beam to control the torsion, and then designing the spandrel beam for the torsion that occurs between the kickers and between the final kicker and the column. Obviously, you'll get some rotation of the spandrel beam in this case, but hopefully the torsion and twist of the spandrel beam won't be so large that it causes significant impact on the design itself. So when we have kickers to mitigate the torsion of the spandrel beam, I think most of us are probably familiar with the kicker concept. We can use a diagonal brace, such as a double angle or maybe even a single angle or a channel, to act as a compression strut to resolve that torsion. So we break the torsion on the spandrel beam down into a couple with a tension force here at the top and a compression force down here at the bottom, and then we have to design the kicker for that load. Now be aware that kicker will have a vertical upward force on the first interior floor beam here, and the slab has to be designed to deal with the horizontal component that's in the kicker load. An alternative to using kickers is to use what I often call a roll beam. This is simply a wide flange beam. In some cases, if it's not supporting the floor deck, in other words, if it's running parallel to the floor deck, it can be useful to depress that roll beam below the top flange of the spandrel so you don't have to cope out the flanges of the roll beam at the connections you see here. And we typically do this by installing a full depth fitted stiffener in the web of the spandrel beam that's welded to the web and flanges of the spandrel beam, and providing bolts here in standard holes, or if they need to be slotted holes, providing slip critical bolts, and relying on this connection to effectively be a moment connection. We're taking the moment or the twist from the spandrel beam out as a couple on those bolts. And be aware that when you do this, you have a vertical reaction upward on the inboard floor beam, and a downward force due to resolving the twist on the spandrel beam. So again, here you see the roll beam with the moment applied to the end. That results in shears in the roll beam that we have to design the connection for here to the spandrel beam and to the inboard floor framing beam. And of course, if you have a deck that's running parallel to the roll beam here, it's okay to depress it as we've shown it here. But in the cases where the spandrel beam is a girder, these roll beams would be simply the typical floor framing beams. And again, here are the notes to that previous slide. So how to deal with the torsion itself on the spandrel beam that we have between the kickers or between the roll beams. AISC's Design Guide 9, which I mentioned earlier today, has some guidance for dealing with torsion on spandrel beams, particularly wide flange sections. And in Design Guide 9, it's assumed that the rotation of the beam in question occurs about the centroid of its shape. So in other words, we haven't translated what we're rotating about. But in the case of a spandrel beam, where the beam is restrained at the top by the slab on deck or by roof deck or other framing, the rotation really happens at the top flange of the beam, as we'll talk about in a second. So AISC Design Guide 9 doesn't really address that. So we've tried to do that in Design Guide 22. And another word on torsion is that we do need to consider the warping normal stresses and the torsional shear stresses, and those need to be considered in combination with the other loads from flexure and axial load and shear that you have on the spandrel beam. For a long time, engineers have known about the flexural analogy method. It's an alternative to the AISC Design Guide 9 method, and the latter might be cumbersome to implement in a spreadsheet. In contrast, using something like the flexural analogy method can be relatively quick to implement in something like a spreadsheet, and I'll talk about how to do that in just a second. In principle, though, the flexural analogy method is to take the torsion that's applied to the spandrel beam and divide it into couples at the top and bottom flanges of the beam equal to the torsion divided by the depth between the centroids of the flanges. So that gives you a lateral force on the bottom flange and a lateral force on the top flange. And then designing that beam for just the T section above with this horizontal force applied, and the bottom T section applied with a lateral force applied to it. Now, this approach can be grossly conservative for long torsional spans, but as I'll get into in just a minute, it actually is relatively accurate for short torsional spans in the order of 10 feet or so. So both the Design Guide 9 method and flexural analogy method would typically consider the spandrel beam to be rotating about its centroid, as you see here. But in reality, that's not what happens in the case of a spandrel beam. In a spandrel beam, the slab laterally restrains the top flange of the beam from displacing, and you get some moment in the slab. It's usually conservative to idealize that behavior as a pin at the center of the top flange of the beam, with the pin only restraining the lateral translation of the beam and the beam undergoing rotation, as you see here, due to torsion. And so that behavior that we need to capture in our design. So again, typical analysis has the beam rotating about its centroid, but for the purposes of what we're talking about today, we're going to assume that the top flange of the beam is restrained laterally for translation, and that there's a pin in the connection between the top flange of the beam and the slab. So when we are rotating the spandrel beam around this pin that we have at the underside of the slab, as I mentioned before, we need to be cognizant of how that rotation affects our facade attachments, particularly if the facade is supported well below the spandrel beam, as you see here. So this is the case of, again, a brick shelf angle supported several feet perhaps below the slab level. And as that spandrel beam rotates, you get a projected translation, a vertical projected translation due to rotation, and a horizontal rotation as well. And those movements will affect the sealant joints that are below the shelf angle right here. And we need to limit those. So in Design Guide 22, we've developed what we call the Modified AISC Design Guide 9 method. It's using all the parameters and charts that are in Design Guide 9, but assuming that the rotation occurs at the top of the beam at its interface with the slab, rather than at the centroid of the beam. And we do the same thing for the flexural analogy method. We call it the modified flexural analogy method. So again, we assume the beam is restrained for translation at the top flange, but is free to rotate. And we take the torsional force and divide it by the height of the beam between the centroids of the top flanges, and we apply a lateral force to the bottom flange and compute what the lateral displacement of the bottom flange is to determine how much rotation we have to design the joints in the facade for. As an appendix to Design Guide 22, we studied a number of different alternatives to study what happens when you put twist on a spandrel beam that's laterally restrained at the top flange. We looked at three analyses. We looked at a finite element analysis. We looked at what we called the Modified Design Guide 9 method and the Modified Flexural Analogy method, and we compared that for two different spans, a 10-foot span between torsional restraints and a 30-foot long span between torsional restraints. And we also looked at concentrated loads as well as uniform twist along the spandrel beam. In reality, the floor slab will provide some restraint against the twist, but we neglected this in our analysis. We assumed that we had a true pin at the top flange of the beam, and the top flange of the beam was only laterally restrained. So again, recall that in the Modified Design Guide 9 method, we're using the parameters that are in the charts in Design Guide 9 to determine the twist and the normal warping stresses, but we're assuming that rotation happens around the center of the top flange of the beam. And when we look at the Modified Flexural Analogy method, we're again assuming that it's rotating about a pin at the top flange of the beam, and we're going to compute a lateral displacement of just the bottom T portion of the wide flange section. And we'll also be using simple elastic theory to determine what the flexural stresses are due to this weak axis bending of the bottom flange of the section. So there are a number of tables that we're going to go through here quickly. They look at a number of different spandrel beam sizes, ranging from a W14 by 30 to a 24-117, and they're going to compare the finite element analyses that we did using SAP to Modified Design Guide 9 method and Modified Flexural Analogy method. And what you'll find is that when you compare the ratios of the rotations from Modified Flexural Analogy method to finite element method, you'll find that for relatively short spans, on the order of 10 feet or so, the ratio of Modified Flexural Analogy method to finite element is much closer than the Modified Design Guide 9 method. Modified Design Guide 9 method is much more conservative and reports much larger rotations. This is specifically for the top flange being restrained. Now if you look at, that's with a distributed twist. Again, when we have a concentrated twist at the midspan, again we find the Modified Flexural Analogy method for short spans produces results for rotation that are much closer to the finite element analysis than the Modified Design Guide 9 method. When we look at longer spans, however, on the order of 30 feet, we find, generally speaking, that the reverse holds true. The Modified Design Guide 9 method produces results that are closer to the finite element analysis method. And that's true whether you have a distributed twist, as you see here, or whether you have a concentrated twist at midspan. again, for longer spans, the modified Design Guide 9 method generally produces results that are closer to the finite element analysis. So for most practical cases, however, where torsional spans need to be kept short to try to limit the amount of rotation that we have in our facade supports, it is generally practical to use the modified Flexural analogy method, and to do that you can extract the forces directly from your analysis software and do some additional post-processing perhaps in the spreadsheet to calculate what the twist due to the torsion is and calculate the warping normal stresses and add those to the stresses, those normal stresses you get from Flexure from your analysis software. So we find this is easier to implement for most relatively short spans. So a few other conditions to consider on spandrel beams. When you have an opening that's adjacent to a spandrel beam, as you might have at a stair or maybe you have at an atrium, there is no backspan and there is no way to address the torsion on the spandrel beam other than to simply design for it or modify the cross-section of the spandrel beam to be more torsionally stiff. And there are a couple of ways to do that. One of which is to maintain the wide flange section that you would typically have, but put a plate on either the inboard flange or maybe even on the outboard flange to turn it into a box section, which will be much more torsionally rigid. And that you really only have to do over the length of the opening. An alternative to that is to use a HSS section, as you see here, in lieu of the wide flange, but be aware this may impact the connections at each end of the column and make those much more complicated, but it's certainly possible to do. Another solution might be to replace the slab altogether with a wide flange section, as you see here, to try to make this section more torsionally rigid. It's a little crazy to do it like this, but it has been done. So there are a number of examples in Design Guide 9 that I'll go, I won't have time again to go through all of these today, but we're going to focus on just a couple of them, looking at what the impact of torsional rotation might be on a spandrel beam. So let's dig into example 6.1, which you see here. We have a spandrel beam supporting just roof decks. This is a non-composite system. We've got an L6x4 angle out here to which the curtain wall mullions, which are spaced at 5 feet on center, are to be attached. So this is a dead load anchor, not just a wind load anchor. The spandrel beam spans 30 feet between columns, and it's a true beam. The deck spans perpendicular to the spandrel beam. So we have no beams to brace it laterally for rotation or translation between the columns. So here's the problem statement again. The beams can be flexurally pinned and torsionally restrained at the supporting columns. We have the roof deck to brace the compression flange of the beam against lateral torsional buckling. We're going to assume that we have these load combinations to investigate for strength and deflection, and we're going to limit deflection to 0.9 inches. So here's a 3D graphic of the loading condition on that beam. We've got a uniformly distributed dead and snow load across the top flange, and we have curtain wall mullion point loads at 5 feet on center along the length of the beam, and those are eccentric to the beam center line by 9 inches. So here's the expression of what the curtain wall dead load is. It's about 2.1 kips at each one of these concentrated loads. There are out-of-plane wind loads here too, but we're not showing those in here just for sake of clarity. So the first thing we're going to do is we're going to try to be 18 by 35. We're going to assume it's A992 material, grade 50 steel. And if we design this beam for strength, we might find this particular one has a demand capacity ratio of 0.41, so it's working with flying colors for strength, as well as for shear, where we have a demand to capacity ratio of less than 9%. So this seems like it's a good candidate, so let's investigate further. So now let's look at what happens when we apply the forces from the curtain wall to the beam and see how much deflection we're getting. First thing we're going to do is we're going to check the angle, this L6x4 by 7/16, for flexure at the tip of the flange, which you see here, and first determine the vertical displacement due to just bending of the horizontal leg of the angle. So when we do that, and we distribute it over an effective width. Again, as we did before, spreading that out over a 45-degree angle, we find we have an effective width of 12 inches, and we compute the moment of inertia for that effective width, given it's a 7/16 angle, and find it's just about 0.08 inches to the fourth. And now we need to also calculate the vertical loads on, from the curtain wall as well. These are acting perpendicular to the plane, and because they're eccentric to the vertical leg here, they're acting 2 inches above the horizontal leg. Those also impose a bending on the horizontal leg. And we find that when we do that, we get the vertical displacement of the leg about 0.02 inches. So this is very small, and this we might even consider neglecting, but it's shown here for sake of completeness. Now when we look at the spandrel beam deflection itself, we look at the dead and snow loads and calculate what the vertical deflection of the beam is. That's 0.349 inches. This is just 5 WL to the fourth over 384 EI. Nothing particularly exotic about that. And now we need to compute what the deflection of the spandrel beam is due to the curtain wall point loads acting where they do. Now, I'm considering here that we're looking at just the vertical displacement of the spandrel beam without any torsion to be considered. So in this case, there's no torsional rotation considered here, and we find that we are just about at our deflection limit for the spandrel beam. So this is the dead load on the spandrel beam, the snow loads on the spandrel beam, and the curtain wall vertical loads on the spandrel beam, and the deflection of the angle that we're using to support the curtain wall. So we're right at our deflection limit. So again, this neglects torsion on the spandrel. So what happens if we do consider the torsion on the spandrel? Well, the wind load, again, is eccentric to the top flange, and the vertical load, the gravity load of the curtain wall, is also eccentric to the spandrel beam. So these combine to impose a torsion on the spandrel. What does that do? Well, when we run through the numbers, which we go through in detail in the design guide, design guide 22, but I won't have time to go through today, we find that the beam member still works okay for flexure. Right? We're 104 kip feet demand over 354 kip feet capacity, but we also have to consider the warping normal stress, which you can get using the design guide 9 method, and dividing that by phi Fy and combining that to our flexural stresses. We're at about 0.84, 0.85% of capacity. We have to look at the shear and combine that with the torsional shear from design guide 9, and we would find that we were at 0.52% of capacity. Now let's look at the rotations we get. We're going to sort of cut to the chase a little bit and move up to a W21 by 50, so a larger section than we were just looking at, but everything else remains the same. So vertical deflection is 0.473 inches to start with. So we've got a stiffer section. Now what happens due to the twist? So using design guide 9, we would calculate the rotation of the section, and we'd look at that rotation and how much horizontal displacement of the angle we had, and find that the angle here displaces a large amount due to the rotation on this 30-foot long span. It rotates such that we get a projected vertical translation of 1.83 inches, which is quite large and much larger than we can accommodate. So even though we have a heavy W21 by 50, it has substantial rotations, and clearly we're going to somehow have to find a way to address the rotation of the spandrel beams. So one way to do that is by using another way to do that is provide kickers or braces, and we'll get to that in just a second. For comparison, if we were to use the modified flexural analogy method instead of the design guide 9 method, we'd find we get an even larger rotation. So as we said before, the modified flexural analogy method is excessively conservative for longer spans on the order of 30 feet or so, but is it more appropriate for short spans? So going back to our example from before, now we've got some roll beams that are perpendicular to the spandrel. You see them here highlighted in yellow. They're depressed from the top flange, so we don't have to cope out the top flange, but we do have to strip the flange from one side. We've got a full depth stiffener and some bolts that we have to design for the moment that's imposed on the roll beam. So in this case, we've got the torsional force that we have to apply to the end of the roll beam, and that results in reactions on the inboard adjacent roof beam as well as a downward load on the spandrel beam. And when we run through the math for this, which we do in much more detail in Design Guide 22, we find that the rotation at the midspan between the roll beams is much, much smaller. It's on the range of 0.75 degrees. And the warping normal stresses are also greatly reduced, as you can see here. So the 21 by 50 that we have here is adequate for this load. Now a quick look at the roll beam itself. We're imposing a moment, a fixed moment, or a concentrated moment, excuse me, on the end of the roll beam, as you see here, and you get this deformed shape to it. And you have to figure out what the rotation of the roll beam is. It's really quite small because you're bending this about its major axis. And find the total rotation of the spandrel beam plus the roll beam is 0.83 degrees. And that results in a vertical translation of just about a 1/16 of an inch. So the roll beams have really stiffened up the spandrel beam for rotation, and we're able to use a lighter spandrel beam. And we end up with a vertical deflection of 0.85 inches when you consider the deformation to deflecture as well as the displacement of the angle curtain wall attachment. You end up with 0.86 inches, which is less than our criteria of 0.9 inches. And just a quick word here on the modified flexural analogy, which, as I mentioned, is appropriate when you've got relatively short torsional spans. You end up with a vertical deflection on the order of 0.19 inches of the bottom flange laterally, and you turn that into a rotation by dividing that by the depth of the spandrel beam and taking the inverse tangent of it. So the rotation of this spandrel beam is 0.61 inches, which is a bit less than we calculated using the modified Design Guide 9 method. So that's it for spandrel beams themselves. Let's talk about supporting facades away from floor levels for just a couple of minutes before we take some questions. And you can have conditions like this at atrium or at lobby spaces where it's necessary to provide perhaps gravity and lateral support to a cladding system, most commonly aluminum glass curtain wall, where you need to restrain the out-of-plane movement and also support the gravity loads. But unfortunately, you don't have a slab edge to help you distribute those loads to the base building structure and the diaphragm. So some quick comments on this before we wrap up. For curtain walls, we typically limit the out-of-plane deflection to the span over 360 or 3/4 of an inch maximum. There may be reasons why you need to do something less than that in these cases. And frequently, whatever steel elements that you provide to laterally support the curtain wall, as you see here, are architecturally exposed structural steel, so you may need a higher level of finish on these elements. You may also need some hangers to support them for gravity load to try to keep their bulk in the vertical direction to a minimum. So you might need some sag rods or some hangers to support those. And let's take a quick case study at one of my current projects. This is a building that has a 2-story space, but the glazing transitions at about midway up the building. So I don't have a floor slab back here to brace the bottom of this facade panel. The building has a panelized facade system, but it transitions from curtain wall to the pre-panelized facade system at the middle height of this 2-story space. And so in that case, I needed to provide some girts or lateral support, as you see here, to laterally restrain the facade panel out of plane, and also to support the curtain wall head that you see here. So this horizontal element spans between posts, which you see here, and those posts span from the floor up to the underside of the structure above. And what's important here is that you provide deformation compatibility in this post by providing a slip connection at the top of the post to allow the floor framing above to displace downward and not load the post in compression. So here's the elevation view of what I was just discussing. We've got a horizontal element that laterally braces the panels and the curtain walls at a plane, which spans horizontally to posts, which span from the floor to the underside of the floor framing above at this lobby space. And that's all I have for you today, and I'll open the floor for questions and turn it back to Nate.
All right, thank you, Alec. We do have some questions from the audience, and as a reminder, you can submit questions for our speaker in the chat feature located on the left of your screen. But first, before we get to questions from the audience, we'll go ahead and do a couple of polling questions to test the audience. The first polling question is a true or false statement. That statement is as follows. To calculate torsional rotations, spandrel beams that support floors or roof decks should be assumed to rotate about their centroids. That statement true or false? Again, the statement is, to calculate torsional rotations, spandrel beams that support floors or roof decks should be assumed to rotate about their centroids. You can put your answer in by selecting the proper radio button on your computer screen. So looks like most of the results have come in. So we'll go ahead and close the poll. And Alec, it looks like about 85% of the class agrees that that is a false statement. Did they get that question right?
Yes, they did. False is the answer that we were going for here. As I mentioned, the top flange of the beam is laterally restrained by its attachment to the slab, or in some cases to roof deck, so that it can't laterally displace, and so that we are assuming that the beam is forced to rotate about that attachment. So it does not rotate about its centroid, it rotates about the center of its top flange.
All right, good job. So let's go ahead and do one more polling question and see if that one's any more difficult. So question is, which of the following composite spandrel beam deflections cause the joints in the facade to close? Is that A, live load deflections, B, rotations due to torsion, C, concrete self-load deflections, D, beam self-load deflections, E, both answers A and B, or is it F, answers A, B, C, and D? And that question is, which of the following composite spandrel beam deflections cause the joints in the facade to close? All right, it looks like most of the answers have come in. So we'll go ahead and go and close that poll. And it looks like about 84% of the participants selected E as the correct answer, and about 10% selected F as the next most popular answer. What's the correct answer here, Alec?
The answer that we were going for was answer E, both A and B. So live load deflections will cause the joint to close as the spandrel beam deflects under flexure, and rotations of the spandrel beam B due to torsion also cause the joint to close, since those will occur after may occur after the joint is set, particularly due to wind loads and so forth. The beam self-load deflections and concrete self-load deflections occur prior to the joint being established, and so they don't have an impact on the joint itself.
All right, thank you, Alec. So let's go ahead and dive into some of the questions that we got from the audience. And our first question brings us to slide 17. And the question is, would it be an option to extend the slab into the structural part of the wall so that there is no moment over the inner beam?
I'm not sure I understand the question. Extending the slab into the wall.
Perhaps I think maybe the question asker is looking for some reinforcement going into the wall, sort of providing fixity between the slab edge and the wall, is the way I understand it.
I see. I suppose that you could do that, though it's probably not going to be particularly economical in terms of coordination of the reinforcement in the wall. And in addition, I think you're still going to have, regardless, I think you'll still have some negative moment over the spandrel beam as well that you have to contend with, and providing reinforcement in the slab to do that.
All right. Our next question will be on slide 38. So here you show a photo of showing this adjustability with the erection fastener and the slot. The question is, what length of slots do you typically see used in these situations? Are short slotted holes typically sufficient, or do you usually look for something longer?
So provided that you're not relying on a slip critical connection between the bent plate and the beam flange, you can actually use a very long slotted hole here for erection. I've specified as much as a 3-inch long slot to allow for a great deal of adjustability. The condition here that you see in the photograph is in fact not a spandrel beam. It's at an elevator opening. But the concept is the same. You want to provide lots of adjustability in the field, and then when the final location is established, then this gets field welded and the erection fastener isn't doing anything at that point. So I usually specify a slot even longer than a long slotted hole.
All right. So our next question will be on this example 5.6. And the question is, should the wet weight of the concrete be accounted for in sizing the bent plate and the weld attachments of the bent plate?
In this case, yes. But I think the example problem that we had was specifically for a roof example. So I don't think that we had concrete in this example, though I could be wrong about that. I'll have to go back and check my slide. But if there is concrete on the deck, then in that case, you would have to consider the concrete load as well. I take it back. There is concrete in the deck, so it should be included in the analysis of the bent plate and in the welds. So we'll pick that up for the next revision, Nate.
All right. That's no problem. So slides 69 and 70, there was a question here where you show this deflection design check. And the question is, should the deflection due to the brick be considered when comparing to the 3/16 criteria? It looks like only the SIDL and LL deflections were considered. So can you comment on whether the brick deflection should be considered or why they weren't?
Okay, so the 3/16 deflection criteria that's shown here was intended to limit the amount of movement imposed upon the sealant joint below the shelf angle. So if you're looking at about 3/16 of an inch of movement, if I have a compressibility of the sealant of 50%, that means I'm starting with a 3/8 inch wide soft joint, which is not uncommon for a brick veneer system. So the deflection of the brick itself will occur prior to the sealant being installed in the joint. So you do not have to consider the deflection of the brick in this particular deflection criteria. It's conservative to do it, but you don't have to do it.
All right. Next question, we'll go to slide 114. And the question is, does the roll beam place torsional rotations on the inboard beam with this strategy? I believe the inboard beam meaning the first interior beam.
Right, that's a good question. Typically, no. We usually provide a double angle connection or a simple shear connection to the adjacent interior beam that isn't intended to restrain or provide a rotation to the interior beam. So all we're doing is providing a vertical shear reaction upward at the adjacent beam.
All right. So let's actually stay on this same slide for the next question. And this question makes use of the word kicker, but we'll pretend these roll beams are kickers in this case. And the question is, in addition to providing lateral kicker, a portion of the tributary distributed torsion goes to the shear tab connection. I believe that is referring to the shear tab connection to the column. Do you typically add a kicker here, or how is that dealt with?
So in terms of the connections to the column, you would have to consider the twist on the spandrel beam translated through whatever connections you make to the column. Now, you can do that through, say, a double angle connection, and that would be similar to what Design Guide 9 refers to as a torsionally pinned connection. So you'd have to take it out as a couple in the bolts, for example, between the double angle and the column, and design the angles for that twist as well. I suppose you could use a shear tab to the column as well, but you'd have to design the shear tab for the twist. But by minimizing the torsional span by providing roll beams, you can minimize the amount of twist that you have to take out of the column. I suppose you could add another roll beam or kicker relatively close to the column to try to minimize that force.
Now there's a question on example 6.1, which, let's see here. And the question is, the rotation is considered here about the top flange. However, in cases, do you consider that cases with only a deck and a deck connector are sufficient to restrain the top flange? And I think the question asker is saying as opposed to when there's a full slab involved.
So when the deck is perpendicular to the perimeter beam, as it is in this case, I would say the deck is probably adequate to resist the lateral translation of the beam. You're putting the deck in tension in its strong direction. If the deck were parallel to the beam, then I could see that the deck wouldn't be particularly effective at restraining the lateral translation of the top flange of the beam. But on the other hand, if the deck were parallel to the beam, you would have additional infill beams perpendicular to the spandrel that would help restrain its rotation and translation. So to summarize, I think that the deck, depending upon its orientation, if it's perpendicular to the spandrel beam, is probably adequate to restrain the lateral translation and force it to rotate as you're seeing here. If the deck is parallel to the spandrel beam, then probably not, but you would have other beams probably framing into the spandrel beam that would do the job for you.
All right. Let's go back to this Appendix A study. And the question is did you ever in this study determine a length where the design guide method, where there's a transition between the design guide method being preferred versus the modified flexural analogy method?
That's an excellent question, and I can't say that we investigated at what point one becomes more effective than or more accurate than the other. We really only studied the 10-foot and 30-foot spans, but that being said, I think the point here is that for most torsional spans, most spandrel beam spans on the order of 25 to 30 feet, you probably need to consider using a kicker or a roll beam to restrain the torsion. And when you do that, you're probably looking at a torsional span on the order of 10 to 12 feet or maybe 15 feet, in which case the modified flexural analogy method is probably adequate to use.
All right. So we'll do one last question here, and it sort of ties in what you were just talking about. Given this result that you show here in example 6.1, the question just is, in your practice, do you typically then go for shorter torsional spans than trying to make spandrel beams span their full, say, 30-foot length, or do you ever try to make those 30-foot types of lengths work for a torsional span?
In my practice, I almost always break up the span with roll beams. I don't use kickers all that often, though, particularly on roof decks, where I might be trying to put the upper end of the kicker into roof deck, which doesn't have much capacity. I almost always use roll beams, and I do it for a couple of reasons, particularly on roof decks. One, because I need to restrain the torsional rotation, but two, I use a roll beam because it laterally braces the bottom flange of the spandrel beam against lateral torsional buckling, which you might experience in a wind uplift case. So providing a roll beam laterally restrains the bottom flange of the beam, not only for torsion, but also for a lateral torsional buckling. For most floor framing, I will typically provide a roll beam perpendicular to the spandrel beam, in part to deal with the lateral forces on the spandrel beam from the facade connection. So not just the torsion, but also for the out-of-plane load. And I generally try not to span the full 30 feet because I find the member size just becomes excessive when I try to do that.
All right. Well, thank you, Alec, for the answers to those questions. And there are some questions that we weren't able to get to. So if you submitted a question we didn't get to, we'll work with Alec in the coming week and look to provide some answers to those folks via email.